And then I told you this is a simulation. So I used Fluka, which is a fully integrated particle physics Monte Carlo simulation package, which is free, of course. And you might wonder why I use simulations. Well, in the if you say, like, if you are going to set up a carbon or proton radiation therapy facility, it costs you like $1 billion, right? So before you're putting in money to the table, you have to have an idea about what you are going to do and what are the outcomes of this project. So what will happen? So that is why, like, we use as scientists, we use this simulation method so that we can validate and we can predict what will happen actually, right? So just for the completeness, I gave this code, and this is what I use. So this is the modulator, and this big green box is the body, and the small one inside is the tumor, right? So this is the basic geometry, right? And then this is how I validated my results. So this graph shows you actual data taken from GSI Germany. GSI Germany, they have a proton and carbon radiation facility over there, and you can see that this result is pretty much goes with my result. So this is so they use carbon 250 MeV per particle. Again, I also use the same energy, and same for the protons. And you can see that my results here and their results are pretty much tally. So now I know my result, my research, I mean my simulations are in the correct path. So then why I chose to investigate about neutrons. So you might see this, after the Bragg peak, there's a tail here, right? So we call this fragmentation tail. This contains fragmentation particles, for example, neutrons, C10, C11, H3, right? Those kind of fragmentation particles. So if you take the radiation weighting factor, right, you can see that for the neutrons, it's like 20. So the biological hazard from the neutrons are much more compared to the other particles. So that's why I chose to study about the neutrons. So this is to find neutrons. So I try to figure out stray neutrons. I mean, this is the neutrons produced from the carbon or proton radiation therapy, stray neutrons. Dose equivalent per therapeutic dose, we call it H/D, inside the body. So for that, this is the body. I took like 30 centimeters water, what do you call that, simulation. And so here A, here A is the pencil beam. Pencil beam is like 1.5 centimeters diameter carbon beam. And then I took these small boxes. So I basically calculated H/D in every 5 centimeters inside the body, right? So B is the water phantom, right? Okay. So this is what I found out. Carbon has this red dots. They are for carbon. I mean, stray neutrons, H/D value for carbons, and whereas these blue dots are stray neutron dose equivalent per therapeutic dose for protons. So you can see that H/D values for carbon is higher compared to protons. So unfortunately, I couldn't found any linear relationship here. I couldn't found any linear relationship inside the body. Why I am interested in linear relationship means like any linear relationship or any simple relationship, so that we can easily guess or easily calculate what is the H/D values inside the body. But we couldn't find any simple relationship inside the body, but outside the body, this kind of stuff. Okay. Outside the body, you can see that I took up to 2 meters level, because that's the from the patient to 200 centimeters maximum length. I calculated HOD values. So you can see that again carbon has higher HOD value compared to protons, but there's kind of like a linear, like a simple relationship that we can get an idea of. If we have a simple relationship, then we can calculate. So now with more data and more results, we can find a linear relationship, right? And finally, now again, let me come to where I started. So comparison of dose distribution for protons and carbon with gamma. So these are the plus points. So less damage to healthy tissues and organs, right, as I explained, and direct action due to high LET. So I didn't have much time to explain about the direct action and the indirect action. Normally photons or the X-ray or gamma rays, they have indirect action, whereas these protons and heavy ions, they have indirect action. These have direct actions. These have indirect action. So direct action due to high LET, linear energy transfer, and greater control and precision. And I showed you like we can nicely spread out the break and we can precisely hit the target. And then in carbon therapy, the other advantage is that as in the tail, fragmentation tail, it release C11 and C10, where they are radioactive and you can track them, right? So you can easily track the path of the radiation, which is a very good thing when it comes to treatment. So, and downside is carbon and proton therapies produce stray neutrons, and we have to study more about stray neutrons. And conclusion, carbon has a sharper Bragg peak compared to proton, where precision is higher towards the edge of the tumor. Stray neutron dose HOD is like 3 times higher in carbon compared to proton, and there are some advantages in carbon and proton radiation therapy compared to photon radiation therapy. These are some of my references. Thank you.